Hello everyone, you are welcome to today's lesson, and in today's lesson we are going to discuss how you can properly size your breakers in all parts of your solar system. And in this lesson we are going to look at the breaker sizing between your solar panels and your charge controller. We are also going to look at the breaker sizing formulas. We are also going to look at the NEC safety recommendations for sizing a breaker. We're also going to look at the AC and DC breaker sizing. Basically, all of the breaker sizing is DC breaker. It's just few AC breakers that we are sizing most at times in solar system. And in solar system, most of the current we deal with is DC current, although we have AC current, but the breakers for the AC side is just for the inverter input and the inverter output. So in this lesson we are also going to look at the common mistake you should avoid when sizing your breakers, and a lot of installers have been making this kind of mistake. So I'm going to walk you through some of these mistakes that you should avoid when you are sizing your breakers. Now before we start, let's discuss why we need breakers in a solar system. Before we start calculating breaker sizing, let's first understand why breakers are important. A breaker is a protective device designed to disconnect power whenever excessive current flows through a circuit. Now, your breakers help to protect cable from overheating. It helps to protect your solar equipment such as your inverter and your battery bank. Breaker also help to reduce fire risks because it can isolate a fault circuit. Now, one important thing many people don't know sometimes, or they misunderstood, breakers are mostly sized to protect your cables. However, breaker does not only stop at protecting your cable, they can also protect your solar equipment, because if excess current flows through your cables and that cable overheated and it results to fire, that fire can also damage your inverter, even though the inverter can isolate itself. However, if the fire is coming from outside, it can still affect your inverter. Now let's discuss the NEC rule for breaker sizing. According to the NEC recommendations for continuous loads like solar system, breakers are usually sized at 125% of their expected capacity or their expected continuous current. That is why we will be multiplying it by 1.25, that's the 25%, to add an extra 25% for safety headroom, and also to help unnecessary tripping, to protect the breaker from tripping off regularly. That's why we don't allow the breaker to work at 100% of their rated capacity. And the formula for this is the actual breaker current multiplied by a safety factor of 1.25. For instance, if you are using a 10 amps breaker, 10 amps breaker, you multiply this 10 amps by 1.25 in order to add additional safety margin for this 10 amps, which is recommended by the National Electrical Code, the NEC. And this is the formula: the breaker size equals to the actual current multiplied by a safety factor of 1.25. Now we are going to look at the first breaker we are going to look at is the breaker between your solar array, your solar panels, and your charge controller or your hybrid inverter, for those who are using hybrid inverter. And the formula for this calculation equals to the short circuit current of your solar panels multiplied by the number of parallel strings multiplied by the safety factor of 1.56. Now for this panel we are using 1.56 because 1.25 1.25 for the NEC recommendations, and another 1.25 for over-irradiance, because your panels can operate more than their STC, more than their standard standard test conditions. In maybe in sometimes they can operate more than that, so you have to put that one into consideration also. And you have to oversize your breaker, because when these panels start operating at this more than their rated capacity, your breaker should be able to withstand the excess current that is coming from your solar panels. So the formula is the short circuit current of your panel multiplied by the number of panels in parallel multiplied by the safety factor of 1.56. Now for this example, we are using two parallel strings, and we are assuming a short circuit of 13.6 amps. Our breaker size will be the 13.6 amps, that's our short circuit current, multiplied by the number of panel in parallel, which is 2 for this example. It will give us 27.2 amps. Now if you apply the safety factors of 1.56, you multiply this 27.2 amps by 1.56, it will give you 42.4 amps. Now the breaker size we are using for this between our solar panels for this particular example will be 45 or 50 amps DC breaker. Why are we using this 45? Because the standard breaker sizes, you may not get this exact size, this exact 42.4 amps. So you choose the next available size in the market, and for this example we are choosing 45 amps or 50 amps DC breaker for this example. Now this is the standard breaker sizes. As you can see, there is no 42 here or 44, it's only 40, 45, 50, 60 and the rest. And based on our outcome is either 45 or 50 amps. So we are choosing either this 45 amps breaker, or this 50 amps breaker, DC breaker, because the current coming from the panels is a DC current, so we are using a DC breaker for this example. Now the next breaker size is between the next breaker we install is also between your charge controller and your battery bank. And the formula for sizing this breaker equals to the controller current rating multiplied by safety factor, which is 1.25 according to the NEC recommendations. Now for this example we are using 120 amps charge controller, and our breaker size will be the controller size, which is 120 amps multiplied by the safety factor of 1.25. Sorry, I made a mistake here. It's supposed to be 1.25 here. I put 1.2, so this one is 1.25. It will give us 150 amps. Now if for your system, if you are using 80 amps breaker, you multiply that 80 amps by 1.2. If you are using a 30 amps breaker, you multiply that 30 amps by 1.2. Why we are multiplying the controller output current is because no matter what your charge controller is generating, the controller cannot push out power more than its rated capacity. Like for example, this 120 amps, even if our panels is generating more than this, the charge controller cannot supply or cannot push out more than 120 amps to your battery bank. So you multiply this one times 1.25, and for this example it gives us 150 amps. Now our breaker size for this particular example is 150 amps breaker, and it should be 48 volts because we are using a 48 volts system, and it's DC breaker, not AC breaker. DC breaker, 150 amps DC breaker. Now for this breaker sizes, we are choosing 150 amps here for this particular example. 150 amps DC breaker between our charge controller and battery bank. Now the next breaker is between your inverter and your battery bank, and the formula for sizing this breaker is your inverter VA multiplied by your system voltage multiplied by the inverter efficiency multiplied by 1.25. Your inverter VA is your inverter rated capacity. You divide it by your system voltage. Sorry, I used multiplication earlier, it's division here. You divide it by the system voltage, you multiply it by your inverter efficiency, you also multiply it by a safety factor of 1.25. And for this example, we are using a 5 kVA inverter and a 48 volt system. Now our breaker size will be the 5 kVA, which is 5000 watts. If you convert kVA to watts, it will give you 5000 watts. Divide by 48 volts, which is our system voltage for this particular example. You multiply it by our inverter efficiency, which is 0.9, that's 90%. Now, before we do this division, you first of all do this multiplication. You multiply this system voltage by the inverter efficiency of 0.9, it will give you 43.2. Then we divide the inverter power, which is 5000 watts, by 43.2, it will give you 115.7 amps. Now there is something I want to bring your attention to here. If your inverter is 2 kVA, you put 2 kVA here. This inverter VA is your inverter capacity. If your inverter is 2 kVA, put 2 kVA. 5 kVA, put 5 kVA. 10 kVA, put 10 kVA. And for the system voltage, if your system voltage is 12 volts, you put 12 volts. If it's 48 volts, you put 48 volts. And for the inverter efficiency, you can check your inverter data sheet. You can see the efficiency there. Then you include it here. Then you multiply whatever the your spec, whatever specs you are putting on here, you multiply it by the safety factor of 1.25. After that, you for this example, it gives us 115 amps. As we can see here, we have not multiplied here yet. The multiplication is this place, is as this place here. This place, you can see, multiplied by 1.25, it gives us 144.6 amps. 144.6 amps between our battery bank and our inverter. Now we may not get this exact breaker size, so we choose the next available size in the market, which is 150 amps DC breaker. 150 amps DC breaker. Because the voltage, the current between your inverter and your battery bank is a DC current, so we are installing a DC breaker here, not AC breaker. Please take note of this. Do not forget. And the standard breaker size here is 150. As you can see, we are installing it. There is available. This size is available here, 150. So we are installing 150 amps DC breaker between our battery bank and our inverter. Now the next breaker size, the next breaker we install is between your inverter and your distribution board, and the formula for sizing this breaker is your inverter rated power multiplied by your inverter AC output voltage. You multiply it also by a safety factor of 125. And using our example, we are using a 5 kVA inverter, and our breaker size will be the 5000 watts divided by the output voltage of 230 volts, and it will give us 22 amps breaker. 22 amps, sorry. You multiply this by 1.25, it will give you 27.5 amps. So it will give you 27.5 amps. You may not get this exact breaker size, so choose the next available size, which is 30 amps. And for this output, like I said earlier, is AC current we are dealing with here. So you install AC breaker here for your inverter output or your inverter input. Please take note of this. Inverter output is AC voltage or AC current, not DC. So you install a 30 amps or yes, a 30 amps AC breaker here, not DC breaker. So you see from our example here, we have 30, 35, 40 and the rest. So we're installing a 30 amps AC breaker between our inverter and our distribution boards. You can install the same 30 amps for the inverter input. You can install the same 30 amps for the inverter output. So the next example is the inverter to your AC load. So for example, for this formula, the breaker size is, the formula is the load, your total load power divided by your AC voltage multiplied by the safety factor of 1.25. And for this example, if your load is 4,000 watts on a 230 volts, your breaker size is the load, your total load, which is 4,000 watts, you divide it by the voltage, which is 230, it will give you 17.4 amps. Now if you multiply it by 1.25, it will give you 21.7 amps. Let's check if you can see this breaker size. No, there's no 21, so we need choose the next size, which is 25 amps. Choose 25 amps. As you can see here, 25 amps AC breaker, not DC breaker, because we are dealing with output current from your inverter. Now, one of the mistakes people make is oversizing their breakers. Let's look at this example. For instance, let me clear this drawing. For instance, this 4,000 watt load at 230 volts, they can draw a current of 21.7 amps. 21.7 amps. Let me just say they can draw a current of 25 amps. Now, if you oversize your breaker, if you not use maybe you install a 50 amps here, and your cable can only handle 20 amps. But this is the breaker size that you install. This is the 25 is the one you're supposed to install, and this is the one that you install because you want to oversize it. Now, and your cable that you install, they can only handle 20 amps. Now, when there's a flow of current, 25, maybe a 25 amps flow of current through this cable, you know the cable cannot handle this, but this breaker can handle this 25 and 45 amps. But this cable cannot handle this 45 amps. The cable will catch fire because of the excess current, and this breaker will not do anything because the breaker can allow 45 amps to pass through it because it's a 50 amps breaker. Now this cable will catch fire and your inverter or your house, the house will now burn, which is the most expensive mistake you should always avoid. Do not oversize your breaker. When your breaker is rated at 25, the most you can do is maybe 30 amps, and that should also depend on the cable you are installing there. If you are installing a cable that can handle 25 amps, then you can install a 30 amps breaker. If you are installing a cable that can handle 20 amps, you can install a 25 amps. Do not oversize it, installing 50 amps because you don't want it to be tripping off. If the breaker is there and is not doing any work, then it's useless and it's very risky for that. So please do not oversize your breaker. If you are oversizing it, it should be within the range. It should be within the range, not outside the range. That's mistake number one. Then mistake number two is oversizing your breaker. Let me clear this drawing. So the undersizing your breaker. Now for this 4,000 watts of load at 230 volts, they are drawing 25 amps on a go. Now if you come here, let me clear this drawing as well. If you come here and install a breaker of 15 amps on a load of 25 amps, now and your cable can handle up to 20 amps. Now when your client put on this load, and this all together, the load, they on everything at once, and this load start drawing this massive 25 current, at once, and then your breaker is only 15 amps. Because this 25 current cannot pass through this breaker without the breaker tripping off, the breaker will keep tripping off, and your client will keep calling you that fire is light is going off in the house. Anytime you on this, maybe you on this AC, the light will now go off. You don't understand what is going, whereas the problem is from you, the installer. You install a 15 amps breaker while you're supposed to install a 25 amps breaker. You undersize it to 15 amps, maybe because you didn't see a 25 amps, or maybe your supplier tell you that no, there's no 25 amps. Instead of you to go somewhere else and look for it, now you went ahead and buy the 15 amps and install, and now the client just on his AC, and suddenly the breaker just trip off because it cannot allow more than 25 amps to pass through it. And sometimes this may result to the breaker overheating. The breaker will now start overheating, and it may lead to something you will not fit explain. So always do not oversize or undersize your breaker. Make sure you are staying within the range. If it's a 25 amps, the highest you can do maybe is 30 amps, because as you can see, we have already multiplied by 1.25, so we have already oversized it. So we are just looking for the next available size in the market, not to size it to maybe 40 or 50 because you couldn't find this 25 amps. So you should always take note of that when designing your system. Now another mistake is installing DC breaker while you're supposed to install AC breaker, or installing AC breaker while you're supposed to install a DC breaker. That's a very wrong habit as an installer. Make sure if you are dealing with AC current, make sure the breaker you are installing there, you are installing AC breaker. So if you are dealing with AC current, make sure you are installing AC breaker, and if you are dealing with DC current, make sure you are installing a DC breaker. Because your client will not know doesn't mean that you should go ahead and do it, because he doesn't know which one is AC or which one is DC. Doesn't mean you should go ahead and do it. Make sure you do a very clean job, that tomorrow your client fit call you back or refer you to another person. Because if you install a DC breaker while you're supposed to install a AC breaker, when the current passing there is a AC current, the breaker will not do anything. The breaker will fail. Because of what? Because it's not meant for AC, it's meant for DC, or because it's not meant for DC, it's meant for AC. So take note of this. I hope I'm not confusing anybody here. What I'm trying to say is the current between your inverter to your house, like that's the output current of your inverter, is AC current. So if you are installing breaker here, make sure it's AC rated breaker. Now between your solar panel and maybe your charge controller is a DC breaker. So if you are installing a breaker there, make sure it's a DC breaker. Do you understand, ba? Make sure it's a DC breaker, not AC breaker, between your solar panels and your charge controller or your hybrid inverter. And between your AC load and your inverter output is AC, make sure it's AC current. So make sure you're installing AC breaker here and not a DC breaker. I thank you for watching, and I hope this lesson will help you understand how you can properly size your breakers in different parts of your solar system. And if you have any suggestion, comments, or question, please drop them in the comment sections, as we are all learning. And thank you for watching. Don't forget to follow for more practical solar installation lessons. Thank you very much. Remain blessed.